Hello everyone, I'm Mingyuan Xia from Mingyuan University, and today I'm going to present our work on making Android application auditing more efficient and also more effective. So this is the screen when you want to install a new Android app. It will pop up with the permission it requires. So here you see that this app will access your personal information as well as want to perform full network communications. So by looking at this, have you ever wondered if this app will leak your personal information via network communication? So if you're not, you should, starting today, because nowadays a smartphone app can access all kinds of your privacy concerned data, your text messages, your contact, your payment information, location, your schedule, and your browsing history. So data leaks are commonly related to a source and a sink. So you can, for example, for an app, you can get the phone number from a source API. Then you can transform this phone number into a URL, and then you call this URL.open connection to leak it. So here, app auditing aims to uncover those data leaks in apps. And a fine-grained one should be able to tell you not only the source and the sink, but also the form that the data will be leaked. For example, here it's unencrypted HTTP GET. It also shows you domain name and the components where we'll leak this data. So there are definitely a lot of use cases for such app auditing tools. For example, your app developers can check their app before releasing them, so they won't be using any data leaking libraries. Also, app market operators will want to scan those apps, newly uploaded apps, to make sure the data leaking ones are not entering the market. For mobile users, you can install app auditing tool on your smartphone. So when you install new apps, you can check it before using it. So all of these use cases have various requirements on the app auditing tool. For example, the app developers want to see all the data leaks in the app. App market operators do not want to have false positive. They don't want to blame anyone who is not leaking. And mobile users do not have that patience to wait the tool to run long, so you expect the efficiency of the analysis. So if we look back into the existing tools, we can for sure perform dynamic analysis. For example, Tentdroid, which is a modified Android operating system with a dynamic tent analysis tracking your sensitive data. However, dynamic analysis has a limitation. It's largely dependent on the user inputs. So if a user clicks on a button, then the analysis will only look at the path following the click button path, and has low coverage as a result. On the contrary, we have static analysis, for example, app intent and a flow joint, which can take a look at the entire app and outline all of those data leaks. However, the limitations for these tools, they have false positives, and they could be very time-consuming in face of real-world applications. Why is this so? Because nowadays, the Android apps are becoming way complicated than usual. And a typical app has tens of thousands of functions, which is millions of instructions that has to be examined. Today's static analysis tool, and they're all performing whole program analysis, will need to have an analysis time in the scale of minutes or hours, and having a great amount of memory to run these tools. And definitely, these tools are not practical for mobile users right now. So in this work, we propose AppAudit, which want to solve the problem with static and dynamic analysis. We present a sequence of two analyses, and we want to make static analysis faster with some false positives. Then we use a dynamic analysis to remove them. And the dynamic analysis, it cannot be performed automatically, so we propose approximated exclusion to tackle this problem. So this is how AppAudit works in a high-level picture. So if it takes raw Dalvik bytecode, which is the Android Java bytecode, perform a fast coarse-grained static analysis, and it finds suspicious function that could leak data. For sure, because it's a coarse-grained assessment, so it has false positives and also actual leaking functions. Then we use this approximated exclusion to examine each of those functions. It's a dynamic analysis, and it will confirm that the data will actually being leaked. And because it's a dynamic analysis, in a sense, it relies on executing this function to confirm leaks. So it's much more efficient than static ones. And also, we can examine multiple functions in parallel to further improve performance at this stage. So we will first look at our lightweight static analysis. The goal is to find suspicious functions. So here, as we remember, a function can leak data only if it can reach a source API which gets the sensitive data, and also a sink API which can leak it, can transmit the data out of the device. So here we use a call graph structure to find functions that can reach both a source and a sink API. For sure, there's a lot of practical challenges, for example, the virtual call reflections, and we simply extend those call relationships to result in an overestimating call graph. This call graph can be constructed and analyzed efficiently, but it has some false positive as a result. Next, we depend on our dynamic analysis to remove those false positives. It's called approximated exclusion, and the high-level description of it is automatically and approximately execute a suspicious function to confirm that the data will be leaked. And its goal is to mimic the real execution of the function. It's approximately because when we are executing a function without any knowledge of its user inputs, we will have unknowns, which is not real. Here, I will show you a running example showing you how this approximated exclusion happens. So for example, we want to run this full function, and when we start running, and we have no idea what x is. So we do not know its type, and we do not know its value. So here, we introduce an object representation. We assign x with an imaginary unknown object, which represents an object that exists before the execution. Then we come to the first line, the source API, which can be something like a get phone number. It returns your sensitive data. It returns the integer of your phone number. And we tint it. It's like a dynamic tint analysis. It's a tinted object contains your sensitive data. It's assigned to x.m, so m now points to this tentative object. Next, we created a new object, y, which we know for sure it's of the type of my class, and we know its field m is for sure 0. Then we derive from x.m and to generate a new object. U is derived from a tinted object, so it's still tinted. Next, it's assigned to y.m. Now the y object, which is a non-object, its m points to u. Finally, we come to a condition. So it tests if x is equal to y. By definition, here, y is a non-object, which is created after the execution, and the x is an unknown object, which exists before the execution. So we can, for sure, evaluate this condition to true. And it comes to the sink API, which we checked, and see that there is tinted object going out of the device, and it's a leak. So the approximated exclusion, as I show you, this looks like on the source code level, but it's actually running bytecodes, and have 15 rules to manipulating the unknown object representation we have proposed. It keeps executing until it finds a leak, it will report, or the function is terminated with no leaks, or it can encounter some unknown control flow conditions, and the details can be found in the paper. The result of the approximated execution engine is, first, it has no false positive because it's actually running this program. It's like dynamic analysis. Every leaks we encountered will be true in the real execution. And also can 100% find all the deterministic leaks. Deterministic leaks means that if there's no conditions for those leaks, and most real-world leaks are like that. And for external input-dependent leaks, we might or might not find all of them. So for evaluation, we assess AppAudit in 3 perspectives. We assess its correctness and its usability in terms of analysis time and memory consumption. And for correctness, we use the open malware dataset, which contains malwares of well-characterized leaking behaviors. And also use a benchmark. For the usability of this tool, we examine it, we use it on malwares as well as real-world applications. Also, we want to share with you some insights we find from the real leaks we found in real-world applications. First, the accuracy. The malware dataset contains over 1,000 samples, and we are comparing AppAudit with the other two static analysis tool. AppIntent is symbolic exclusion based, and FlowJoy is flow graph based. So you can see that AppAudit is leading the accuracy in this game. And we have missing 0.7% are all false negatives. They are all external input dependent leaks. There typically, there is a malware function which pings a phone number, then waits for its callback, and then leaks its data. Since the analysis is done without the knowledge of the external sources, so that's the false negative. I want to highlight this negative case. And this negative case, well, both of the previous tools marked it as a false positive. Only AppAudit is successfully identified it as a true negative. So this case works like this. So this malware has a configuration file which is encrypted by a customer DS with a hard-coded private key. It returns a string, then it passes it and obtains a list of URLs that it will send your sensitive data to. However, this specific case has a malformed configuration file. After passing it, it gets no URLs. So there's no leaks will happen in real. And only by doing approximated exclusion, we run it, and then we decode this configuration file, perform all the parsing. We know that there won't be leaks at all. So for the usability side, we first assess the analysis time. For AppIntent, it's not publicly available. We only reference its results from their paper, and we have no results on real-world apps. It's way beyond 1 hour. It's out of the scope of the competition. For FlowJoy and AppAudit, both of them perform faster on malwares because malwares are smaller than real-world apps. And for FlowJoy, when it encounters real-world applications, it takes more than minutes to examine each of them. And well, I don't think mobile user can stand that long to get this result. AppAudit returns immediately when it's examining malwares. And also, for real apps, it takes around 5 seconds each. On the memory cost side, and both of the static tools are whole program analysis. They maintain large analysis data structure of the entire program. It's according to their paper and also our evaluation, they take several gigabytes to examine per app. For AppAudit, it's execution-based. It's not whole program analysis, so it takes around 200 megabytes for each app at most. And we argue that the AppAudit is the only solution which is practical for running on a mobile device right now. Finally, I want to share with you some real leaks we found in real-world apps. We examined 400 real apps, and we find 30 data leaks. All of them are manually confirmed, and there is no false positive. The detailed list is in the paper, but I would just want to share you some insights of them. So all of these leaks combined has 500 million installs, and I personally have some of them installed on my device. So first we want to take a look at what app components actually leaks the most. We find that the answer is the ads library. And when we look at the privacy policy of these apps, only a few of them mention third-party libraries. So this makes a case for developers to use app auditing to check their apps before releasing them to get to know what your ads library are doing. Next, we examine the sources of the data leaks. Real-world apps will leak 3 kinds of data. 2 of them are tracking tokens, and the last one is location. Although we checked around 15 kinds of leaks tents, these are the only 3 found in real-world app. It makes sense that ads library wants to use them to customize their ads. Finally, the venues of those leaks. We surprisingly found lots of those leaks are plain text HTTP requests. They're not encrypted. Everyone on the network can see your data encoded in a URL. And a few of them are using HTTPS. And the HTTP is the dominant way of doing these leaks. So these results, the 30 data leaks, are discussed in the paper. We have set up a cloud scanning infrastructure, AppAudit.io. We now have scanned over 140,000 apps, and we have uncovered more than 8,000 data leaks. It takes us slightly less than 2 days to finish all of them with 3 medium-class blade servers. The work in progress we have, we want to improve this tool towards more auditing details. For example, we want to inform the user when this leak will happen. For example, when you click on a button, then something will leak. We will provide that information in the future version. Also, we are working on the mobile and the developer tool side to make AppAudit more useful for more users. And I do have a simple Android port for the AppAudit tool. It's running on my Nexus 5 tool, but it's still too ugly to show you guys, so I'll skip that. If you're interested, you can come to me after the talk. And here it's the look at the AppAudit.io results. And we have 3 cases which has all data leaks. And we also check with virus total and check with their permissions. And that concludes my talk. Thank you very much.
Time for some questions.
Oh, sorry, yeah. I do have a Q&A list, which is if you happen to ask one of them, just tell me the number.
Let me see.
That's great.
Okay, so actually I have a 9th question, if you don't mind. So I'm JP from EPFL, Switzerland. The question is the following. The very notion of leak is, actually this is maybe relatively close to question 2, but still with a different flavor. Depending on the context in which a user is, he or she will be annoyed or not of having the information leaked. Right? It will depend essentially on what circumstances, the location, the time of the day, with whom the person is, etc. So how do you take, do you take the dimension into account in some way?
Yeah, that's a good question. Currently in our tool, it's not in the scope, but we have some thoughts on that. And the subjectiveness of leaks are quite hard to characterize in real. Right. But for example, the external input dependent leaks, they rely on some external inputs. And they say, well, if it is from a trusted source, then you think it might not be leaking your privacy. If it is from some unknown networks, then it's a leak. So it's a hard question, but we have some thoughts on that. And for example, we can provide a whitelist of those external sources. So if, for example, if it is from a well-known, like your carrier or the well-known trusted websites, then it's not a leak. Otherwise, then it could be.
Right. Okay, we'll also be interested in question 6, but maybe we should leave time for the other.
Hung Ying from Syracuse University. So my question is about the Android apps is unique in terms of the multi-entry points. And some activity can only be triggered by intents and system events. Mm-hmm. So do you have particular handling to trigger certain entry points and then start to execute or not? Because if you don't do that, you'll definitely cause false negatives.
Thanks. We do have handling of those cases. We have the handling both in the static part, also in the dynamic part. In the static part, we will complement we will extend the call graph in terms of those intent, receiver, and the life cycles. And at the dynamic part, we will emulate what Android will do for those callbacks. For example, you're clicking on a button, then your callback will be scheduled, and we will execute it just like real executions.
Okay, thanks.
Eric Der, CISPA Saarland University. I guess it's a follow-up question. So I was wondering, how can you distinguish that code from code that is actually reachable? So for instance, in third-party libraries, you have a lot of functions, whereas only a small fraction of these functions is really used in the app. And if you have some leakage within this, third-party library, how can you be sure that this is really executed?
Yeah, that's a good question. So yeah, I agree. There are a lot of that code is not at all called by the by the application. So, but consider two cases. For example, first you receive an intent, and you will have trigger all this life cycle method of Android. So we can have a reachability test to see how to see if some code will be reached. That's the first case. On the second case, if the app has a reflection call, then that code might be called in some cases. So we cannot firmly say, well, that code will never be touched at all if we have reflections. And that's not uncommon in Android apps.
Yeah, but I was thinking more like virtual method calls. For instance, you have a very imprecise call graph, which you say, okay, if there's a virtual method call, then you assume that it could be any class that could be the receiver. And if you would have a more precise call graph with some type inference, you could eliminate those false positives.
Well, that's a trade-off. So we really want to make call graph simple as possible because we have the dynamic analysis to examine that. And while we have, in previous work, for example, FlowJoid, it has a really accurate flow graph to model all those calling and also data flow and control flow transitions. But we are a different trade-off space as compared to those cases.
Okay, thank you.
Thanks.
All right, let's